Okay, we're back. Day 2 of Voronoi diagrams. Right, so what we saw recently was how we make a series of sites, which are basically ordered pairs, on a Cartesian plane, connect them with line segments, and then how do we find the perpendicular bisectors. Those bisectors, interpreting them properly, outlines for us what the Voronoi diagram will look like. Remember, the Voronoi diagram edges tell us the places that are halfway between any 2 points. Basically, all the points on the line are equidistant from the sites that it splits, and so they represent the boundaries of the Voronoi. So let's why does it keep doing that? Let's continue here. Now, here I'm going to be using some of these bits of vocabulary, so I want to make sure we're reminded. This is a screen capture from our previous video. We have various sites. Those are the coordinates A, B, and C in this particular case. The perpendicular bisectors will eventually become boundaries or edges, and they demarcate some regions, which we call cells, and where they all meet is called the vertex. Okay, so we got those vocabulary points down. Here's a cute little video I saw. Some guy making a Voronoi diagram by hand. And cool music, too. Try to make all the line segments so that none of the lines cross, but you're connecting to all the sites that are nearby. Every one of those line segments will need a perpendicular bisector. You will never be asked to do something this big, unless of course you choose something like this for your IA, then you might. Now he's just doing this by eyeball, which is to approximate. So he's taking the midpoints here of all the different sites, measuring them, going halfway, dropping a line. So he's not using an electronic approach. All the midpoints are found. He's going to start drawing in the perpendicular bisectors. And again, it's by eye, so it's an approximation, so it won't be perfect. Represent a pretty impressive final piece of work when he's done. You make sure those perpendicular bisectors cross. Notice that the three cross at the same point. Any three nearby perpendicular bisectors will always cross at the same point. It's called the circumcenter of a circle. Let's speed that up a little bit. Examination shows you which ones are creating the cells. They can't overlap. You just gotta think about it there. Okay, we're not doing that, but we will do these questions. So we're in the final section of exercise of chapter 4. This is exercise J. Now we're not really, when this video concludes, we haven't quite done the theory yet. There's one more thing we need to do, which is the concept of largest circle, and its famous name is the toxic waste dump problem. That sounds pretty ominous, but it's actually pretty cool. Okay, so there's 3 questions there to do, and I'm going to do a couple. It says demo down there at 4J. I'm going to do the first 2, but I'm going to leave the last one for you because I think it's really important that you try and practice at least on one of these things. Okay, so here's the first question. I've sort of splayed out the questions in the top part there, so the video will fit down below. It says in a town, there's 3 schools, A, B, and C, and they're located at those coordinates, right? We're going to place a new school in town that we want to be as far apart from the existing schools as possible. Okay, so there's 4 parts to this: A, B, C, and D, and here we go. Let's take a look at the video that I made to support this. I've already created a Cartesian space that's big enough to accommodate it all. So first thing I'm going to do is put all the points down. Geometry. I need to list them by coordinates. And I've left them exposed at the top of the screen there. 1, 3, 6, 4. Open a new set of brackets. 6, enter, 4, enter, and 6, 1. Okay, so there's escape the mode, you're in the mode, there we go. So now you can see all 3 schools there. I'm going to join them up with line segments now. So I go to line segments, and I just tap on the point to be at one end of the line segment. I tap on the other point to be at the other end. Tap on C to start one, B to finish it. I can go back to C to start the last one and end up at A to finish it. Okay, escape that mode. Now I need to find the perpendicular bisectors. We're actually on to part B now of the problem. Find the equations of the perpendicular bisectors of AB and BC. Not all 3, just 2. Remember that all 3 are going to connect at the same place anyway, so it doesn't matter. Now, there you have it. Now you can see, I did all 3 actually. You can see that they would have crossed at the same point, just that the calculator doesn't offer a long enough line segment to see it visually sort of happen there. Going to find the equations of these lines. I'll find the one that separates A from B. There it is, negative 5x plus 21. And y equals 2.5. That's a horizontal line, slope 0. Escape that. I can see what they are now, but I need to find where they intersect, because that point will, I had to go check something on another page there. That will be where the new site should go, because it's furthest from A, B, and C, because it's the end of the radius of the circle that connects them. If you deviate from that point, you're going to be closer to either A, B, or C. So we don't want to do that. All right, let's continue here. Make a new page. I'll go to a calculator page. I'm going to find out where those 2 lines actually cross so I can reveal the coordinates. And I just set the equations equal to each other. So it was 2.5 for one of them, and it was negative 5x plus 21 for the other. Say that you're solving for x, comma x, and it tells us that the x value will be 3.7. Now that doesn't tell us what the y value is, but the y value we know is 2.5. Because remember, one of the lines was y equals 2.5, and every line on it, every point on that line has a y value of 2.5. So I'm going to graph them because I can't find the intersection on that graph, on that Cartesian plane. So I'll type in the actual line, and it superimposes. And I'll type in another one called y equals 2.5. And now they cross. So I can go ahead and visually locate the intersection of the blue and red lines now by using a graph analyze mode 6. Where do they intersect? Option 4. And just surround those 2 lines. You can see, not surprisingly, the point is 3.7 and 2.5, which we had more or less already concluded. Now the last thing I want to do is find out how far, that's point D of the problem, how far. So I go back over here. One of the options is measurement, option 3, and I can find a length. And I just tap on any 2 points and it will tell me how far apart they are from one another, from A to the point of intersection. I could have done from B to that point, or C. And it says 2.75 U. It means 2.75 units, whatever those units are. Those are just the markings on the axes. So 2.75. I'm going to go calculate that too, just to make 100% sure. So we're going to find the difference in the x values between A and the intersection point. The point was 1, and the x value of the other point was 3.75. And this is the distance formula. We've done that before. Plus the y values were, you can look it up here, 3 and 2.5, and square that, and it tells us it should be 2.75 like last time. And you can see this is much more precise now, but we don't need it to be that precise. 2.75 will be sufficient. And so we've answered the entire problem. Where should the school go? School should go at 3.7 and 2.5, and it will end up being 2.75, was it miles, kilometers, something, from the other schools, exactly the same as all the other schools. Okay, let's try to question number 2 now. At a fair, there's 3 different hamburger stands. The fairground is in the shape of a rectangle. Dimensions, it's 100 wide, 50 high, let's just say. Bottom left corner of the field can be regarded as the origin. Okay, we'll call it 0, 0. And so then we've given the opposite corner, of course, 150. Got it. 100 on the x, 50 on the y. And the hamburger stands are located A, B, and C. Let's take a little picture of what that looks like. So here they are. Now, I put this little flyer up here. Can you get this on your GDC? This is student survival mode now. Do you have the tech capability of actually putting those ordered pairs onto a Cartesian plane and being able to see them? If not, hit pause and make sure you can do it and ask for my help if you can't. Okay, now what I've done is I've made the perpendicular bisectors between A and C and B and C. Now, I know they don't appear to be particularly perpendicular to the line that connects A and C or B and C, and that's because I've adjusted the scale so everything fits in nicely. It's no longer a square scale, meaning it's not just as far on the x-axis as the y-axis, so it looks a bit like off, like it's been twisted a bit, but don't worry about that. It actually does represent the perpendicular if the scale was returned to square. Now again, can you do this on your own GDC? If you cannot, stop and get some help to make sure you can find the equations of those lines. Right, now we're going to draw the Voronoi diagram. So I need to know where those lines cross each other. Now, whoa, lots happened there. I didn't go through the whole video of this, just did screen captures because we just did it in the last example. I went ahead and I drew the lines, which were shown, revealed in the last slide. And they are y equals x minus 10, that's shown in blue, and y equals negative 2x plus 140, which is shown in red. And I also did the final one, which is the perpendicular bisector that joins between A and B, even though it wasn't presented in the last slide. And that is the vertical line, x equals 50. And you can see I also found out where these three lines cross each other, and that's at 50, 40. It would be the center of a circle that would connect A, B, and C together. Therefore, it is the farthest you can get from A, B, and C because it's equally distant from A, B, and C. If you were to move to any other part, you could get further from one of them, but you will get closer to another point, and that's what we want to avoid. Okay, let's move on now. So I've labeled point D, and I've taken away all the other things that were getting in the way. It was looking very cluttered. So now it's a much more clean look, and that's where D should go. That's the point that's furthest from A, B, and C. And that's probably where you want to put your hamburger stand. Now, the last thing I did was I also put a vertical line at x equals 100 and a horizontal line at y equals 50 to sort of demarcate where the edges of the fairground are. Find the region of the fairground which is closest to C. Well, you can see that's going to be in this zone over here. And closest to A, that's going to be this zone over here. So a fourth hamburger stand is to be added at the point that's furthest possible, and that's going to be D. And again, just like before, because the scale has been changed to accommodate that rectangular fairground, that doesn't look much like a circle, but it actually is. It's been elongated because the scale has been adjusted. So I'm going to go ahead and change it back to a square scale. That looks a lot more representative. You can see the Voronoi diagram, those line segments in there. How far will the new stand be from the other stands? Well, I can go ahead and do the distance. Now, again, I found the distance between point D, which is at 50, 40, from point A, whose coordinates are 20, 30. Use the distance formula, and I can see I'm 31.6 meters away from A and from B and from C, and that's the farthest I can get from each of those other points. Okay, so as this came up recently, someone was asking about what exactly do we need to know and how can I present this information, because it's not clear. This is a new topic for sure. Let's just go over some of the highlights here. You need to know how to find sites, vertices, edges, and cells, and you need to know what those different words mean. You need to be able to add a new site to an existing Voronoi diagram. We've done that in the last video in this one. The nearest neighbor interpolation, well, that's just that incremental algorithm to insert a site in there. Here's some further guidance for students and teachers. It says examinations coordinates of sites for calculating the perpendicular bisectors will be given. So you won't have to go back and sort of reverse engineer, find out where the sites were from an existing diagram. Students will not be required to construct perpendicular bisectors, so you don't have to manually make them yourself. Technology will help, of course. It's much easier if you know that command. Questions may include finding the equation of a boundary. That is the equation of the perpendicular bisector, by the way. Identifying the site closest to any given point. So if you find a point within a cell, knowing that the site that's in that cell is the closest one. And you may be asked to calculate the area of a region, and that, of course, is finding the area of a triangle or some sort of quadrilateral or other thing. And that will be clear in the time ahead. So where does that leave us now? Let's go back to our list of questions in 4J. I've done 1 and 2 for you, and you can see I've circled 3 down there. I'd like you to try that one by yourself, and we've got the rest of the lesson today to try that. Please do get it on your GDC, transfer the information over to paper. You can highlight or identify exactly what's important and what's not, and then it should be good to go from there. And now we're going to take a look at the final piece of the puzzle in our next lesson, which is the so-called toxic waste dump problem, and then that'll be it. Then we've covered all of chapter 4. Okay, talk soon.